All right, so when you're going through these problems, it's a little hard to understand why you're doing these different steps. It's almost like you have to see the result and then you work your way backwards. But you'll get to this point, you'll see which of my directions is the homogeneous boundary conditions. This is the equation you want to get to. Okay, the one with the plus lambda squared. Okay. All very confusing so far, but any questions? Yeah. At this point, no, right? Because when we're solving these two problems, only x is appearing in one and one in the other. So they actually are just ODEs. Right? Okay. Okay. Let me just make sure I didn't miss anything here. All right, so then step 3. All right, step 3 is called solve the eigenproblem. So how many of you have heard of eigenproblem, eigenvalues? Yeah, some not. Okay. So what this is doing now is we've come up with this equation. The solution to this equation is a periodic function, right? It's sines or cosines, as you'll see in a second. So when we're talking about finding a solution, like what's the solution to sine of x equals 0? Well, there's infinitely many of them depending on where you are along x, right? So an eigenproblem is a problem where there's basically infinitely many solutions, but the solutions all together give you the single solution. Okay, so we're going to end up having an eigenproblem where we have infinitely many components of the solution. We just then have to put them back together. Okay, so step 3. We're generating this eigenproblem and then solving it. So, all right, so this equation here, the solution to this, if you go to Maple or you're really good with ODEs, the solution to this is Tx is C1 times sine of lambda x plus C2 times cosine of lambda x. Lambda times x. Lambda times x. Right, that's the solution to that ODE. All right, so we need to then apply the boundary condition. So we have our solution for x. Let's apply boundary conditions. Where do we get the boundary conditions? Well, let's go back to the problem and let's look at the boundary conditions in x. All right, so for the first one, let's see, what was that? It was Tx equals 0 equals 0, and then the other side was the differential at x equals w equals 0. Okay, so first boundary condition, t at x equals 0 equals 0. So if we are to enforce this boundary condition, we can't just enforce it for t of x because t of x is only half of the full temperature. Right? It's only one part of the full temperature. So we need to enforce this for t of x and y. Okay, so then we're saying this is true for t of x times t of y. However, if we were to choose and say, okay, how do we get the temperature at x equals 0 to be 0? It could either be Tx is 0 at that location, or Ty is 0. Well, if Ty is 0 at that location, then Ty must be 0 everywhere, right? And that's not interesting. That's not really a helpful solution. So we're going to enforce this boundary condition on the piece that we know is meaningful. Here we're going to say Tx equals 0 is actually mapped to Tx at x equals 0 equals 0. Ty can be whatever then, but Tx at x equals 0 has to be 0. Okay, so we can plug in, let's see, what do we do? So, okay, that's the first boundary condition. We'll come back to actually plugging it in. The second one is differential t with respect to x at x equals w equals 0. Right, again, we're applying this for both the x and y components of temperature. But in order for this to be meaningful, we want to just consider the x part of it. Okay, so we would say, okay, ty is constant as a function of x, so that comes out. So it just becomes ty times dt dx at x equals w equals 0, right? If ty is constant as a function of x, that can be divided out, right? And then this becomes our boundary condition here. Right, so we have these two boundary conditions now that we can actually enforce. Okay, so we better get through this so you have enough to do your quiz. All right, so let's see, let's go through this. I'm enforcing this on step 1. We're going to say tx at x equals 0 is equal to c1 sine lambda at x equals 0, right? Plus c2 cosine lambda at x equals 0. That has to equal 0, right? So that's just saying tx equals, right, c, let's see, this cancels out c2, right? Because cosine of 0 is 1, so that equals 0. So we end up saying c1 times sine of lambda x. Right, this is our kind of progress here. So we've canceled out the second term because of that boundary condition. Okay, continuing on then for the second boundary condition, we have the dx at x equals w. Okay, so plugging that in, now we have c1 times the derivative, which is lambda cosine of lambda times w. That has to equal 0. So this is saying cosine of lambda w has to equal 0. Okay. When is that true? When is cosine of lambda times w 0? Well, it's true a bunch of times. Right? This is true when lambda times w is equal to what, pi over 2? It's also true when it's equal to 3 pi over 2 or 5 pi over 2 and so on, right? Infinitely many times it's equal to 0. So right, this is where we get this, the eigen part of it, the eigenproblem part of it. All right, so then we would say, all right, let's call lambda now lambda I. So lambda with index I is going to be equal to the values 2 times I minus 1 times pi over 2w for I equals 1, 2, 3, and so on to infinity. Right? Do you see where this came from? Right. So we get pi over 2. So if I is 1, that's 2 minus 1 is 1 over 2 times w. Right. So that's just pi over 2. Right. If I is 2, it becomes 3 pi over 2. If I is 3, it becomes 5 pi over 2, and so on. And so we've come up with an index for indexed lambda that gives us all these values, right? These eigenvalues. Okay, and then the step here, the last step I think we'll be able to get to is to say that tx now is for the ith eigenvalue is equal to c1 times c1 at the ith eigenvalue times sine of lambda I times x. Okay, so what we have here is these here are the eigenvalues. Okay, the condition that gets us those eigenvalues up here is called the eigencondition. The eigencondition. And then the original function that that we use to enforce this is called the eigenfunction up here. Okay. Any questions on this so far? And I know it's kind of complex, but okay. Okay, so that yeah. So that gets us, I think we're out of time. We'll continue on this on Wednesday, and we'll kind of go through the rest of how you solve this problem. Thanks.